Sushruta for NEET is now available on the Google Play Store. Try it out for free.
So good morning, students. Let me first describe what we have learned in our last class. Everything I'll describe just in a brief, and then I'll move to the topic that I have decided to teach today. What we have in the last class we have learned about the adsorption isotherm. We started with the friendly adsorption isotherm, and this equation we have studied about x by x by m is equal to kp to the power 1 by n, where n is greater than 1. This x by m is called the extent of adsorption, and this is equal to kp to the power 1 by n. But what we have seen, if you take the logarithm of this equation, a logarithm on the both hand side, and then if you draw a plot between log x by m and log p, you should get a straight line. But what we see experimentally, we do not get a straight line, and this is because particularly at higher pressures, we see this equation fails to describe the behavior of adsorption, and that is where what the limitation of the friendly adsorption isotherm. And that if you see this adsorption isotherm, the experimentally obtained adsorption isotherm, what the isotherm means, that this adsorption x by m, extent of adsorption, when it is plotted against p at a constant temperature, that is called isotherm and adsorption isotherm. Sorry. So what we see at the lower pressures, we see the extent of adsorption is almost proportional to the P. And so here you can see, and at the higher pressure x by m, the extent of adsorption is not dependent on the pressure. Adsorption doesn't increase. And so what we see, the value of n is not constant. In that case, this adsorption isotherm do not follow the equation that is given by the friendly. So we see the limitations. The experimental isotherm always seem to approach saturation at high temperature. So this cannot be explained by friendly isotherm, thus it fails at high pressure. Then to just explain the limitations of those friendly isotherm, Langmuir gave the theory, and what he actually talked about, that absorption takes place on the surface of the solid only till the whole of the surface is completely covered with a unimolecular layer of adsorbed gases. And even then he said there are two actually phenomena occur simultaneously during the adsorption. The first is condensation of gas molecules on the surface, and then the evaporation. Second one is the evaporation of the gas molecules from the surface back into the gaseous phase. And then he said these processes are it happens simultaneously at all the time, and so adsorption reaches to the equilibrium that we call the adsorption equilibrium. And with that he gave this equation that the extent of adsorption is x by m is equal to ap, where p is the pressure, divided by 1 plus bp, where a and b are constants, and one can get from the experimental value of this adsorption isotherm value of a and b. But what we see, the Langmuir theory also had such limitation, and this limitation is particularly because he assumed that the unimolecular adsorption only happens when a gas is there a gas interacts with the surface. But what we usually see, that this unimolecular adsorption happens only at low pressures and high temperature. Usually at high pressures and low temperatures, this the unimolecular adsorption or unimolecular adsorption is not, this theory is not valid, because the multiple layers of the adsorption that may form, the molecules get adsorbed one above the another at higher pressure and lower temperature. So this had also certain limitation, but it explains something to a more realistic extent. Now then we studied about the adsorption from the solution phase, and there we studied all the things that we have seen for the adsorption of gases on a solid. Similar things happen, so adsorption of solution phase. We have seen that it also forms the friendly equation. Is the friendly equation is only that what we have changed is the pressure. We have changed pressure to the concentration of the solute. The solute may also get adsorbed onto the solid surfaces from the solution, and we see here is the concentration of the solute, and we have also seen that this equation now it follows its more realistic equation for the absorption of solute from the solution phase onto a solid surface. So this is a more realistic equation, and that we see if you draw a, find a graph between log x by m and log c, usually we get a straight line, and so this equation, the Frenlich adsorption isotherm, holds much better the true, and it actually is much more accurate for the adsorption in the solution phase. And then we show the adsorption application of adsorption, and we have seen the application of adsorption in the gas mass, the separation of inert gases in the dissociation, desiccation or dehumidification is the adsorption and removal of water vapor from a particular pot and the vessel. And so this is desiccation or dehumidification, the removal of coloring matter from the solution. The example we have seen, use of animal charcoal to remove colors from the sugar solutions. In the production of high vacuum, this process of adsorption is used in the curing diseases for flotation process. This thing we will also see later in the metallurgy. Then the adsorption indicators. The examples we have seen heterogeneous catalysis. This heterogeneous catalysis we'll see in more details in the today's lecture, and then the chromatographic analysis as well. We have seen these examples where adsorption is the theories of absorption, and this phenomena of absorption is being used for the particular application. Now let us now study about the catalysis. This is where I'll start the new topics. The catalysis, a little about the catalysis we have already studied in the chemical kinetics chapter. And there we have seen the catalyst, usually they do not change the thermodynamics of the reaction, they only change the rate of the reaction by decreasing the barrier, the reaction barrier. This barrier means by decreasing the activation energy for the reaction. This thing we have seen already. So that if you start this catalysis, the catalyst, those are the compounds that we call catalyst. So now if you start with the example potassium chlorate, the potassium chlorate, when it is decomposed, we require the temperature 653 to 873 Kelvin, then it gets decomposed into KCl and 3O2. And even at this temperature, this reaction happens very slowly. But if you add just some amount, little amount, a traces of manganese dioxide, we see that this reaction happens at much lower temperature and also with enhanced rate. And this is why we see this substance is a foreign substance, manganese dioxide, that is used. It is accelerated, it enhances the rate of the reaction and the decomposition of KClO3. It means, and what has also been observed, that the added MnO2, its amount and also its shape and other things, mass, do not change after the reaction. And similarly, we see the similar examples. There some other foreign substances also enhances the rate of some other chemical reactions. And if you see this example here, the sulfur dioxide when reacts with oxygen in presence of vanadium pentoxide or platinum, it gets converted into sulfur trioxide, and this reaction rate increases multiple times when in the presence of vanadium pentoxide or platinum solid. This is the reaction is very important in the formation of sulfuric acid. So and then if you see the example, this HCl can react with oxygen to form chlorine and water. This is the Decans process. And what is Decans process? This reaction is initially very slow in absence of any foreign substance, but when you use copper 2 chloride or cupric chloride, which is copper 2 chloride, and this reaction rate of this reaction increases multiple times. And this process, this catalyst was actually first used by Decans. So this process is called Decans process. So what we see the systematic study. So what we see the foreign substance when is added uh, with the reactants, it enhances the rate of the given reactions and rate of that reaction. And what we also see that substance, its composition and its amount do not get altered, do not get changed. It means that this foreign substance, its presence only is enough for enhancing the rate of a particular reaction. And the systematic study of the effect of various foreign substances on the rate of chemical reactions was first made by Berzelius in 18. He reported these things in 1835, and he suggested the term catalyst for such substances. And this term catalyst was coined by the Berzelius, and he termed this foreign substances which increases the rate of the reaction without being consumed during the reaction as a catalyst. Thus, the substances that accelerate the rate of a chemical reaction and itself remains chemically and quantitatively unchanged after the reaction is known as catalyst, and this phenomena is known as catalysis. So, enhancement of rate in presence of foreign particles which do not undergo any chemical combination or a chemical change or any in the amount is called the catalysis. So a catalyst, what we have seen in the previous chapter, the catalyst changes the rate of reaction without affecting the overall thermodynamics of the reaction. It means if you see this energy profile of this reaction energy with respect to versus progress of the reaction. A progress of reaction we also call reaction coordinate. This is called energy profile. What we see the reactant is getting converted into the product. In absence of any foreign substance, what we see this reaction barrier is this reactant to get converted into product has to cross this large barrier, and this barrier is the energy barrier, and this barrier is called activation energy. Now when we add a foreign substance that we call a catalyst, what happens, this barrier gets decreases, and once this barrier gets decreases, the possibility of this reaction to happen increases. It means the rate of this reaction becomes faster. And now what we see that however that the energy of the reactant and energy of the product do not get altered. If the energy of the reactant and product do not get altered, means that catalyst does not alter the thermodynamics of the reaction. So if the reaction is spontaneous by a certain extent in the forward direction, it will remain be spontaneous by the same amount in the given direction. So the relative stability of the product and reactants are not going to change, means catalysts do not change the relative stability of reactants and products. It only alters, only changes, means the reduces the activation energy barrier, or this energy barrier of the activation energy of a given reaction. Let us now study about the inhibitors. So as we have seen that there are substances which decreases the activation energy barrier or the barrier or activation energy required for a chemical reaction to happen. How we see that there are also certain substances which increases the activation energy for a given reaction. And so if that substance is added to a particular chemical reaction, what happens, that reaction, the rate of that reaction will slow down, and it will get retarded. And it is why, because the activation energy for that reaction will increase in the presence of that foreign substance, and those substances are called inhibitors, or one particular substance will be called as inhibitor. People also call it as a negative catalyst. So the more accepted, the more widely accepted term is inhibitor. So what we see, a reactant is converted into product. Initially, the barrier in absence of any foreign substance, this barrier was this. So this was the barrier up to here to here. However, if you add certain foreign substances, the barrier increases. It means the rate of that reaction will slow down. It will become slower, and so this foreign substance. It is why, because the activation energy is now increased, as such foreign substances are inhibitors. So the examples of such inhibitors are like this. In the oxidation of sodium sulfite, what happens? What we know, the sodium sulfite reacts with oxygen to form sodium sulfate. But when you add a traces of alcohol, certain amount of alcohol, what we see, the rate of this reaction decreases, and rate of this reaction decreases in presence of alcohol. So the alcohol is inhibitor here for this particular reaction. What we see, alcohol is inhibitor for this reaction. It doesn't mean alcohol will be inhibitor for all the reactions. Like to that, what we have seen, this catalyst, this substance increases the rate of only this reaction. It doesn't mean it will increase the rate of all the reactions that we know. So catalysts usually are very select. This is called the selectivity of catalyst or inhibitor. So we have seen all these examples. The MnO2 catalyzes the decomposition of KClO3, potassium chlorate, and so this is called a selectivity. Now let's see the oxidation of benzaldehyde to the benzoic acid. This is a benzaldehyde. The benzaldehyde is oxidized to benzoic acid, but in the presence of diphenylamine, what we see, the oxidation process slow down, and that is why this diphenylamine is called inhibitor for this particular reaction, inhibitor for the oxidation of benzaldehyde to benzoic acid. The tetraethylate is added to petrol to retard the ignition of petrol vapors. On compression, in an internal combustion engine and thus minimize the knocking at this thing. You know the knocking, we want to minimize the knocking, and to minimize the knocking we use tetraethylate. And how it minimizes this? Because it retard, it slow down the ignition of petrol vapors, and because of the ignition of petrol vapors it retards, it slow down that process, and so the knocking gets reduced. There are also some other terms, the useful terms that are used in this the catalysis processes, and the one example is the promoters, or these promoters are also called activators, and the poisons or the catalyst poisons. So the substances what we have seen, if you add certain substance, we have seen that people have seen that the efficiency of a particular catalyst increases in presence of certain substances, other substances, and those substances are called promoters. Means that substance is promoting the activity of catalyst, it is enhancing the activity of the catalyst or the efficiency of the catalyst, and that is why it is called the promoter or the activator. So substances that themselves are not catalysts, those substances they do not catalyze the reaction, they do not act as a catalyst if they are used in isolation, they do not decrease the barrier. But when they are used in a small quantity with the catalyst, they enhance the reactivity of the catalyst, and thus such substances are called promoters or activators. The examples, if you see in the Haber process, the Haber process is the manufacturing of ammonia. Iron acts as a catalyst, but if you add a traces of molybdenum, we have seen that the efficiency of this process increases, the rate of this reaction increases, and so molybdenum is a promoter in the Haber as a used as promoter for the iron catalyst in the Haber process. In the manufacture of methyl alcohol from water gas, what do you know? Water gas, carbon monoxide plus hydrogen. This thing we have studied in the hydrogen chapter. So, if the in the manufacture of methyl alcohol from water gas, CO plus H2, the chromic oxide, Cr2O3, is used as promoter, and for this process, the catalyst we use is the zinc oxide. So, zinc oxide for the conversion of water gas into methyl alcohol, zinc oxide acts as a catalyst. And then when if you add this chromic oxide, the Cr2O3, in presence of zinc oxide, we see the efficiency or the rate of this process increases, and that means the Cr2O3 is a promoter for the zinc oxide catalyst for the conversion of water gas to methyl alcohol. So this particular reaction, if you add only chromium oxide Cr2O3 and not zinc oxide, you see that it doesn't affect the rate of the reaction of the. But if this Cr2O3, if ZNO is added, ZNO catalyzes this reaction. But if with the ZNO you add little amount of chromic acid, this reaction becomes further efficient, and so this molecule, this compound Cr2O3 is a promoter. It acts as a promoter for zinc oxide catalyst for the conversion of water gas to methanol. This is water gas, CO plus H2 is water gas, and this H2, the reduction, one extra hydrogen we require as a reactant, and so we get methanol. So one can write this reaction. People also say CO plus 2H2 gives CH3OH, although they say this is water gas because, sorry, CO plus H2 is water gas. So now the substances, what we know about the poisons, there are certain substances which destroy or decrease the reactivity or the activity of a catalyst. And so those substances are called catalyst poisons. So substances that destroy or decrease the activity of a catalyst by their presence are known as catalyst poisons or simply poisons. If you look at the certain examples, the presence of traces of arsenic oxide, arsenic 3 oxide, H2O3 in reacting gases reduces the activity of platinized asbestos, which is used as a catalyst in the contact press process for the manufacture of sulfuric acid. So platinum was initially used as a catalyst for the contact process, and the reaction that we see is this. SO2 when react sulfur dioxide reacts with oxygen to form sulfur trioxide, and this platinum catalyst was used initially. But what we see in this process with the air, what we see also the arsenic oxide goes in there, and so it actually poisons this catalyst, platinum catalyst. So later on people started using vanadium pentoxide. So vanadium pentoxide is used because this arsenic impurity that goes with the reacting gases actually poisons the catalyst, and the catalyst, platinum catalyst, in the contact process for the formation or the manufacture of sulfuric acid. So the activity of iron catalyst is destroyed, and another example is the activity of iron catalyst is destroyed by the presence of H2S or CO in the synthesis of ammonia by Haber process. In the Haber process, what we see the use of iron catalyst, but this iron catalyst, its activity is reduced or decreased by the presence or destroyed by the presence of carbon monoxide or hydrogen sulfide. If this hydrogen sulfide or carbon monoxide is there with any of the reactants or the whatever the reactant source for the hydrogen and nitrogen, the gaseous source that we use. If these impurities are there, these impurities destroys the activity of iron catalyst. So H2S or carbon monoxide are poisons for iron catalyst for this process. And the carbon monoxide poisons the platinum catalyst used in the oxidation of hydrogen. So oxidation of hydrogen react with the oxygen to form water, and the catalyst we may use is the platinum, but that platinum catalyst is poisoned by the presence of carbon monoxide gas. Some other terms are also there. So autocatalysis that we talk about. So in some reactions, what has have been seen that one of the products act as a catalyst. There are only few examples like that. So in the initial stages, the reaction is slow. And why reaction is slow? Because initially we have not added any catalyst, but later on, as the products form, one of the product act as a catalyst to the rate of the reaction as the products form increases, it get enhanced. And so this type of catalysis or this phenomena is called autocatalysis. If you look at the example, the oxidation of oxalic acid by acidified potassium permanganate increases as the reaction progresses, and this acceleration is due to the formation of manganese 2 plus ions formed during the reaction, and so the manganese 2 plus ions acts as autocatalyst here. So if you look at the example, oxalic acid when react with KMnO for potassium permanganate in presence of sulfuric acid, we see the formation of MnSO4, manganese sulfate plus this K2SO4, carbon dioxide and water, and this the coefficients are used to balance this reaction that we know. This stoichiometric amount this reaction is happening, and so what we see the formation of manganese 2 plus ion, and manganese 2 plus sulfate, manganese 2 sulfate, this manganese 2 plus ion is formed. This is dissolved in the solution, and so this Mn2 plus ions actually catalyzes this oxidation process. So the Mn2 plus ions act as a autocatalyst, and this phenomena of autocatalysis, because one of the this product, the Mn2 plus ion, acts as a catalyst. So this phenomena is autocatalysis. We also see there are many such examples, although the examples are not as much as we see the examples in the catalysis. For this autocatalysis, there are some more examples. Another example is hydrolysis of ester. If you see this methyl ester, if you hydrolysis of methyl ester may happen if you add this methyl ester into water. Slowly, this reaction gets converted into this direction. So this reaction, this reactant, methyl acetate, it will convert it into acetic acid plus methanol. Initially, this reaction is very slow, but after certain time, what we see the formation of acid. Usually, this reaction, this hydrolysis reaction, happens in the presence of an acid. And if you have, no, we have not seen that example. Maybe it will come later on. So, this methyl this reaction usually happens in the presence of H plus the HCl. So even if you don't add HCl initially, this reaction will be very slow, but after a certain time, once this acetic acid is formed, this is also an acid, and H plus ions or the hydronium ions will be released into the solution, and those hydronium ions then will now catalyze this hydrolysis process. And so this process is also an autocatalytic process, and the catalyst here is the acetic acid that is formed during the reaction, this reaction. So these are the examples of autocatalysis, means the one of the product acts as a catalyst during the reaction, and whenever you see such examples, you can see this process phenomena is autocatalysis, and the product is acting as an autocatalyst, and the phenomena is autocatalysis. We also see some examples of induced catalysis. We see certain reactions do not happen in isolation, but when if you couple this reaction with another reaction, what you see this reaction also happens in the presence of that reaction. And this phenomena, this type of examples are called induced catalysis. So induced catalysis is when one reaction influences the rate of another reaction which does not occur under ordinary conditions. This phenomena is known as induced catalysis. And for example, what we know, the sodium arsenide, it doesn't react with air, but sodium sulfite reacts with air to form sodium sulfate. When you add sodium sulfite it with the sodium arsenide, what we see this reaction, the oxidation of the sodium arsenide also happens. And so a mixture of sodium arsenide means the solutions of sodium sulfite and sodium arsenide, when they are added together, they are mixed together. What we see in the presence of air, this reaction, now we also see the formula of this sodium sulfite will of course get converted into sodium sulfate, but since this reaction is happening, we see this reaction also happens, and so sodium arsenide is converted into sodium arsenate. So this is sodium arsenate, and this process, this phenomena is called induced catalysis, because this reaction induces this reaction. So in presence of this reaction is also happening, and such examples are examples of induced catalysis. Means one reaction is inducing catalysis for another reaction, and inducing the reaction or the rate of reaction for another rate of another reaction. So catalysis generally we see can be broadly divided into two groups, and these are called homogeneous catalysis and heterogeneous catalysis. So remember the term homo, same, homogeneous and heterogeneous. And homogeneous catalysis is what when the reactants and catalyst are in the same phase. It means the whatever the phase the reactant is, if you add the catalyst which is in the same phase, then such catalysis is called homogeneous catalysis. Means this is the way they will form homogeneous mixture, and because they are in the same phase, and so this kind of catalysis is the homogeneous catalysis. And this same phase means this usually solids will not mix with each other, they will not form the homogeneous solution, homogeneous mixture. So usually we see the homogeneous catalysis when reactants and the uh, as well as the catalysts are in the liquid or in the gas phase. And the examples of homogeneous catalysis is the lead chamber process, and the lead chamber process, but we see this is also the process for the manufacture of sulfuric acid. And this SO2 when react with oxygen along with catalyst nitro, this is NO, the nitric oxide are all in the same phase. So what we see, the SO2 is a gas, oxygen is a gas, and NO is also a gas, and they are all in the gaseous phase. They are in the same phase. Hence, this kind of example of catalysis is homogeneous catalysis. The SO2 gaseous reacts with oxygen gaseous in presence of NO gaseous, which acts as a catalyst for the formation of SO3 sulfur trioxide gas, and this process is homogeneous catalysis because these reactants SO2 sulfur dioxide and oxygen are in the gaseous phase, and the catalyst is also here in the gaseous phase in the same phase. So this is an example of homogeneous catalysis. Another example of homogeneous catalysis is hydrolysis of ester. And the hydrolysis of ester, you see here the example, we use HCl as a catalyst. So hydrochloric acid, even if you do not add HCl as a catalyst, this reaction will initially be very slow, but later on this reaction, and as the reaction progresses, the rate of reaction increases, although that rate of reaction may not be as high as this reaction happens in the presence of HCl. So what we see, CH3COOH, this is a methyl acetate in the presence of water. This is hydrolysis. Reacts with this. This is also a liquid. This is also a liquid. Both the reactants are liquid, and the HCl, which is in the aqueous solution of HCl, we use, which is also in the liquid phase, and so they are all in the liquid phase, and thus this is also an example of homogeneous catalysis, and this forms acetic acid and methanol as a product. Another example of the hydrolysis of sugar. But we know the sugar, we use sucrose solution for its hydrolysis. The sucrose is first dissolved in water. The sucrose solution we use, and the solution we are using, it means the water molecules are already there. So one of the reactant will be water because water is consumed during the hydrolysis. And the sugar, although in the form of aqueous solution, and there we use this in the hydrolysis process to increase this process, to enhance the rate of this process, we use sulfuric acid as a catalyst, and sulfuric acid we also use in the liquid phase. And so the catalyst in the liquid phase, the reactants are in the liquid phase. This is the aqueous solution which is in the liquid phase, and this is also in the liquid phase. So this catalysis is also an example of homogeneous catalysis. So just let me put the charger of my laptop. So now the heterogeneous catalysis example. The heterogeneous catalysis is what? When the catalytic process in which the reactants and the catalyst are in different phases is known as heterogeneous catalysis. Usually in the heterogeneous catalysis we use solid surfaces or solids as a catalyst, and then the reactants usually are in the liquid or gaseous phases. And these kind of examples usually are the examples of the heterogeneous catalysis. So the catalyst and the reactants are not in the same phase. Reactants usually are either in the liquid or gaseous phase, and the catalyst is in the solid phase, of the solid state. So the oxidation, the examples, if you look at the examples of the heterogeneous catalysis, the first example we come at the sulfur dioxide conversion of sulfur dioxide into sulfur trioxide, the contact process. The contact process is also the process for the manufacture of sulfuric acid. So we see initially formation of sulfur trioxide in the presence of platinum, which is a catalyst, which is in the solid state. So platinum here, the catalyst is in the solid state, and what we see the reactants, both the reactants are in the gaseous state. And so this is an example of the heterogeneous catalysis. Oxygen is in the gaseous phase. We know oxygen is a gas. Sulfur dioxide is also a gas, but the catalyst is solid. So the catalyst and the reactants are in different phases. So this is an example of heterogeneous catalysis. The combination between dinitrogen and hydrogen to form ammonia, the Haber process that we know in the presence of finely divided iron is also an example of heterogeneous catalysis. So nitrogen reactant and the hydrogen also used as a reactant. They are in the gaseous phase, and this iron is what in the solid state. And so this finely divided iron is also, even though it is finely divided, but each particle, small particles, are all the solids. And so what we see, the catalyst in the solid state and the reactants are in the gaseous state. So this is an example of the heterogeneous catalysis. Means the Haber's process is the example of the heterogeneous catalysis, and where the ammonia is formed from nitrogen and hydrogen in presence of solid iron catalyst. The oxidation of ammonia into nitric oxide in presence of platinum gauze in a Swald process is also an example of heterogeneous catalysis. And what we see, ammonia is oxidized to nitric oxide NO. So ammonia, when it reacts with oxygen, it forms NO plus 6H2 in presence of platinum catalyst, and platinum here is in the solid state. So the ammonia is a gas, oxygen is also a gas, and this catalyst platinum is solid, and so the catalyst and the reactants are in different phases, and so this is an example of heterogeneous catalysis. Another example of heterogeneous catalysis is the hydrogenation of vegetable oils in the presence of finely divided nickel as a catalyst. So finely divided nickel acts as a catalyst for the hydrogenation of vegetable oils to vegetable ghee. And see this nickel as a solid, and this nickel solid, and the vegetable oil we know they exist in the liquid state, and hydrogen is the gas. So one of the reactant is in the liquid state, another reactant is in the gaseous state, and the catalyst is in the solid state. And so the reactant and the catalyst are in different phases, and so this is an example of heterogeneous catalysis. Let's see some general characteristics of a catalyst. Most of these things we have already covered in the last chapter, but I'll briefly just go over and mention these points. So general characteristics of a catalyst is a catalyst does not influence the equilibrium constant. So the catalyst does not influence the equilibrium constant, but it helps achieve the equilibrium faster. So it only reduces the time of reaching the equilibrium by increasing the rate of both forward as well as backward reactions. So only catalyst reduces the time that is required to achieve equilibrium, but it does not affect the equilibrium constant. Means it does not affect the equilibrium concentration of reactant and products, but it increases the rate of forward as well as backward reactions. So it helps in achieving the equilibrium. So equilibrium is attained faster in the presence of catalyst, although the equilibrium constant is not altered in the presence of a catalyst. The catalyst remains unchanged in mass and chemical composition at the end of the reaction, and this is what the definition of catalyst. It remains unchanged, so it is not consumed, and not only it is not only consumed, but its composition, although it is being initially used during the catalytic process, it take part in the chemical reaction, but after the chemical reaction, it get back to its initial uh, structure, and so its chemical composition and its amount are unchanged even at the end of the reaction. And so this is what the catalyst is defined. A catalyst cannot initiate the reaction, it only alters the speed of a reaction. It means if the reaction is not happening between two reactants, it doesn't mean if the reaction is non-spontaneous in a given direction, a catalyst will not alter the thermodynamics that we know. It will not alter the thermodynamics of the reaction. So if there is no possibility for a reaction to happen in a given direction, it will not happen by addition of the catalyst. Catalyst can help certain reactions to happen, only it just alters the rate of the reaction or speed of the reaction. It does not start the reaction in the given direction. It doesn't change the reaction thermodynamics, or it will not make non-spontaneous reaction a spontaneous process. A small quantity of catalyst is generally sufficient to catalyze almost unlimited reaction. And this is why, because catalyst initially take part in the reaction, but after the reaction it is released, and if once it is released, so now it is again ready for the mm, next ready for the next phase of the reaction. So it will now catalyze another molecules, another and so the only a small amount of catalyst is enough for a large amount of reaction to happen. A catalyst is generally a specific, and this is what I have briefly explained earlier. So, a catalyst is generally a specific. A catalyst for a particular reaction. What does it mean? A specific means a catalyst for a particular reaction may fail to catalyze other reaction. Means if you see that this is a catalyst, doesn't mean you use same thing for all the reactions. It will not catalyze all the reactions. It will not increase the rate of all the reaction. A particular compound increases the rate of a particular reaction, and so this is what is called a specificity of the catalyst. So a catalyst for a particular reaction may fail to catalyze other reaction. Also, different catalysts for the same reactions may lead to different products. So what also we see, the different catalyst, a particular reactant has potential to form many different products in different directions. So all those products, the formation of those products, if as the thermodynamics suggests that the reaction in the given direction is spontaneous, but those possibility will not happen until unless because of the high energy barriers you add a catalyst. So if you add different catalysts, different reactions, this reaction will happen in different directions to different products. Thermodynamically, all those products where formation of products were feasible, means they were spontaneous, then only catalyst what will happen, different catalysts for the same reactants may lead to different products. Means the same reactant has the potential to form multiple products, and different products to form different products, it will follow different pathways. And so catalyst, a particular catalyst will enhances the efficiency or the rate of a particular pathway only, enhances that, and so different catalysts will form different products. So there are certain theories for the catalysis, and so let's see about the theories of catalysis. The first theory is the intermediate compound formation theory. So how do the catalyst decreases the activation energy barrier, or how it means activation energy, or it decreases the barrier. So how it affects? So usually, as if you remember, when I explained the catalysis in our last chapter, the chemical kinetics, what I have said that the catalyst they get involved into the reaction. So initially, if suppose a reaction was happening in one step, so once if the catalyst is involved that reaction will happen in at least two steps, and both the steps their barriers are much smaller than the original barrier, that the of barrier for the original reaction that was happening in absence of the catalyst. So the this is what we call the intermediate compound formation theory, and the intermediate compound formation theory, this intermediate compound will be formed with the help of the catalyst. So catalyst will essentially go into the reaction, it will take part into the reaction, but after the reaction it will be released, it will come out of the reaction, and so it is again available for the next phase. So this theory, the intermediate compound formation theory, explains the mechanism of homogeneous catalysis. According to this theory, so homogeneous catalysis, the reactant and the catalyst are in the same phase. So according to this theory, the catalyst first forms an intermediate compound with one of the reactants. And this intermediate compound is formed with less energy consumption that needed for the actual reaction. Less energy consumption is for this formation of this intermediate compound, the smaller barrier is there, the activation energy barrier is lesser. And so this will be formed, this intermediate compound will be formed because the activation energy is smaller for this, the barrier for this reaction is smaller. So the intermediate compound will be formed. And the intermediate compound are not that much stable, and usually thermodynamically they are unstable. So their energy, suppose this is the reactant, so their energy of the intermediate compound will be like this. So this is unstable. So because this is unstable, so it will go further into the next phase of the reaction to form a stable product, and so on the next step of the reaction is also the barrier is smaller, so it will go into the next step, and so the reaction will happen. Finally we obtain the product, and the catalyst is also released during the reaction. The intermediate compound, being unstable, combines with other reactant to form the desired product, and the catalyst is regenerated in the next step of the reaction. The catalyst is now regenerated, and thus is available for the next reaction, to catalyze the next reaction. And so if you take this example A plus B, if it gets converted, it combines to form AB. This process initially, in the absence of catalysis, a catalyst has a very high barrier. Now if you use catalyst, this reaction is also happening. So A plus B is now the product is same, forming AB. This catalyst, then what does it do? The reaction occurs in the presence of catalyst C in the following steps. So this reaction will now happen in at least two steps. This was a one step reaction. So now it will be in the, it will happen in two steps. So initially this was the reaction, the energy profile. Now this reaction energy profile will be something like this. So two steps, two barriers will be there. So what happens? The catalyst initially, just a hypothetical example it is. So catalyst will first react with A, reactant A, to form AC, which is an intermediate compound. Now this intermediate compound, as we know, it is not thermodynamically not not a stable compound. So this AC will now react with B, another reactant, to form AB, and then this catalyst C will be regenerated, released after this. So this is catalyst is regenerated. Now it is available for the next phase of the reaction. And so what happens, we see this reaction is happening in two steps, and the example, the real life example, is the catalytic oxidation of sulfur dioxide to sulfur trioxide in the lead chamber process plausibly takes place as this. The lead chamber process, what we know, we have seen, we use the NO catalyst, nitric oxide, as a catalyst, and this example I think I have already shown. Lead chamber process, the oxidation of SO2 to SO3, the catalyst is NO, nitric oxide. The lead chamber process is the example of homogeneous catalysis, and so this theory also explains the homogeneous catalysis. And so this NO, which was the catalyst, nitric oxide, reacts initially with one of the reactant, which was the reactants were SO2 and O2. So it initially reacts with oxygen to form NO2 gas, and this NO2 gas is intermediate compound, the nitrogen dioxide gas, and now this nitrogen dioxide gas reacts with the SO2 gas. SO2 gas is another reactant, and this is the intermediate compound. This intermediate compound, which is not that stable, will now react with the sulfur dioxide to form sulfur trioxide as a product plus NO gas, and this nano gas is a catalyst. So this catalyst which was consumed here, which was used here, is now regenerated here. And so this again, this will now catalyze the next phase of reaction. So you can see how the catalyst actually, this intermediate compound formation theory is now explained in these examples. So catalysts initially form intermediate compounds which are not that stable, and these intermediate compounds now react with the another reactants to form the product, and then it the catalyst also get released or regenerated. Now the next theory is the absorption theory of catalysis. This absorption theory of catalysis is actually, it explains the mechanism of heterogeneous catalysis. For the homogeneous catalysis, the intermediate compound formation theory is there, and now the absorption theory of catalysis also involves this theory. So other than adsorption and desorption, the theory is already included the intermediate compound formation theory in the adsorption theory of catalysis. We will see the old theory of the old adsorption theory was that the reactant in the gaseous state or in the solutions are first adsorbed on the surface of the solid catalyst. Once they get adsorbed on the surface of the catalyst, their concentration increases, they come much closer, so possibility of their collision increases. This was the theory, and so the rate of the reaction increases. Another point is when they get adsorbed, some energy will be released, and that energy is used for this reaction to cross this activation energy barrier. This is how people explain this adsorption theory initially. The catalytic action after adsorption are similar to that of the intermediate compound formation theory, but then so this point is not that important. So what we see, that reactants get adsorbed on the solid surface, and they get adsorbed on the surface, their concentration increases, and the energy that is released because of the adsorption, because adsorption is exothermic process, that energy is used to cross the activation energy. And so this is the old adsorption theory. Now people have given the modern adsorption theory, and this modern adsorption theory includes the intermediate compound formation theory plus the old adsorption theory. So old adsorption theory plus intermediate compound formation theory, both when they are combined, we get the modern adsorption theory. So it means initially the reactants will be adsorbed onto the catalyst surface, and whether those reactants are in the liquid phase or the solution phase or in the gaseous phase, they will first get adsorbed on the catalyst. After they are adsorbed on the catalyst, the reactants which are closer by, they will combine and they will form the product, and after the product formation, that product will be released out from the surface, and so the vacancy is again created on the surface of the catalyst, and so this reaction will keep happening again and again. So the mechanism of modern adsorption theory involves following steps. These are the steps. First of all is the diffusion of the reactant to the surface of the catalyst. So catalyst surface is somewhere, the reactant might be somewhere else. And because it is a solution and nearby only few molecules will be there. So first of all, the many reactant molecules will be diffused towards the surface, and they will in the next step they will get adsorbed on the surface of the catalyst. So adsorption of reactant molecules. In the next step, the reactant molecules will be adsorbed. The reactant molecules strike the catalyst surface and get held up at the surface by partial chemical bonds, and the partial and the weak chemical bonds, they will get adsorbed there. And this is why, because we see that the surfaces of the solids, usually the atoms which are in the bulk, they see their bonds are saturated there. We see all the valencies are completed, but some atoms which are at the surfaces, their valency, they we see the unsaturation, and so those valencies are still available, and thus we see the adsorption. In the adsorption, we see the chemical bond formation. In the step third, the formation of an intermediate happens. So the particles of the reactant adjacent to one another on the catalyst surface join to form an intermediate complex. They combine, which are the particles of the reactant which are nearby on the catalyst surface. They will join to form the intermediate complex, and now this intermediate complex will decompose. Addition of the intermediate complex will also happen, and the decomposition of the intermediate complex will happen to release the cat, and so the desorption of the product. And after that, the decomposition of the intermediate complex means the activated complex breaks to form the products, and these product molecules now hold the catalyst surface by partial chemical bonds, and so these products will also be having partial chemical bonds, but they will hold the surface initially on the product formation. So this intermediate complex will now break into the products. The products, and these products will now be held at the surfaces of the catalyst. And now then in the next step, the desorption of these products will happen. So desorption of product, the particles of the product are desorbed or released from the surface, and thereby making the surface available again for the more reaction to occur. And then the next step, step 6, the diffusion of the reaction products away from the catalyst surface will happen. So the products that were released just nearby the surface will now diffuse to the bulk of the solution, so that some space will be there for new reactant molecules to come and they will get absorbed there. If the product molecules will be at the surface or near the surface, the reactants, the possibility for more and more reactants to come and get absorbed will be less if they are, because they will hinder the uh, they will hinder the forthcoming of the reactant molecules or diffusion of the reactant molecules near the surfaces, because the products are already there. So the product will now diffuse away from the surface, and so it will create the valency is created. So what we see, unlike the inner part of the bulk of a solid surface or the catalyst, this is what thing I have just explained. The surface of a catalyst has a free valencies, and this free valency, because we see the unsaturation in the valency, because when you cut the surface, some of the bonds which were there with, if the large surfaces are there, you just cut the surface, you can assume, understand that the sum of the bonds will be broken to break a surface, the solid surface, and wherever those bonds are broken, there the free valencies are available now, and these valencies provide the seed for the chemical bond formation or chemical force of attraction with the reactant molecules. When the molecules of gas or the solution come in contact with such a surface, they get held up due to the loose chemical combination or loose chemical bonds. And if different molecules are adsorbed side by side, so if the different molecules are adsorbed side by side, they may react with each other, resulting in the formation of new molecules which are products. Thus, the formed molecule may evaporate, and these formed molecules may first will be dissolved from the surface and so will go away from the surface. And if these molecules are the products are the they are gases, so they will evaporate from the surface, leaving the surface of the new reactant molecules. And if that products are the in the solution or the and they form the liquid, and so they will diffuse into the liquid solution. Or if their products are also solid, so they will go into the solution as a solute. So this theory, the adsorption theory, explains why the catalyst remains unchanged in mass and chemical composition at the end of the reaction and is effective even in small quantities, as it explains that the reactants first they come, get adsorbed, they react, form product, they resorb and go away from the catalyst. So this theory explains also why the catalyst is remain unchanged during a chemical combination. So this illustrative diagram also shows these processes in different steps. So it, however, does not explain the action of catalytic promoters and catalytic poisons. So how the catalytic promoters and catalytic poisons work, this theory, adsorption theory, doesn't explain the actions of promoters and poisons. But the adsorption theory of reactant molecules, let's see how, so if these are the catalyst surface having free valencies, and the free valencies are there, and this valency is the heterogeneous catalyst. In the solid state, it is having free valencies at the surfaces. Those free valencies are not at the bulk, please remember. And the reactants, suppose there are two reactants A and B, they were mixed, they are in the solution, suppose they are in the solution phase. So once they are in the solution phase and the solid small finely divided particles are there, they are sick. So A and B will now diffuse and come closer to the surfaces. And once they come closer to the surfaces, the first step can consider here. And the next step, adsorption of the reacting molecules takes place, and this A and B will get adsorbed, and they will get adsorbed at two different valencies. So these are vacancies positions. They get adsorbed here, and so A and B get adsorbed. These are just an hypothetical example for you to understand the adsorption theory. This absorption theory of catalysis for the heterogeneous catalysis, these 6 steps that I have just explained. So A and B, now they are closer to each other, they may react. So reaction between adsorbed molecules will happen, and so A and B will now form a bond between. So A and B will form a bond between them, a bond will be formed. And now what happens if in the next step, if this another reaction was about to happen, so this may break into different substances if the molecules are there. But since we see the formation of only AB, then the next step, a desorption of this will happen. So AB now will desorb, means will go away from the C surface. It will, this bond, chemical bond will be broken, and then AB bond will further be stabilized. So this will be broken, AB bond will further be stabilized. So it is released, the desorption of ABV is happening in this step. So desorption of product molecules, and from the desorption, after desorption, this product molecule will diffuse into the solution, or if it is a gas, it will evaporate from the surface. It will go away from the surface, and so it will now, this catalyst is now again available for the next phase of reaction to happen. Let us now see the important features of solid catalyst. The important features of the solid catalyst, the heterogeneous catalyst that we have seen, the one is the activity. If you talk about any catalytic process, you also talk about the activity of the catalyst, because this activity, if the activity of catalyst is high, the rate of the reaction in the presence of that catalyst will be higher. So a particular reaction, there can be many catalysts, and the efficiency of different catalysts or the activity of different catalysts may differ. So if what we see, the activity or the rate of reaction in the presence of a particular catalyst is higher, means the activity of that catalyst is higher than the other catalysts that also catalyze this particular reaction. The catalyze means what? In absence of any foreign substance, any catalyst, this reaction was very slow. And if you add a substance, even if the rate is increased 1.5 times, 2 times, that is also a catalyst. And if you add another substance and it increases the rate of the reaction 1,000 times. You add another substance and it increases the rate of the reaction 10 to the power 5 times. So the substance which increases the rate of the reaction 10 to the power 5 times, that activity is highest among the three catalysts that have the same. So this is what we call the activity. The activity of a catalyst is its ability to increase the rate of a particular reaction. And if its ability is higher, means it increases the rate of a particular reaction to a higher extent, it means its activity is higher. So chemization is the main factor in deciding the activity of a catalyst, and what we have seen here, the chemization takes place, chemical bond formation is happening here. So chemization is very important, is the main factor in deciding the activity of a catalyst. The adsorption of a reactant on the catalyst surface should be neither too strong nor too weak. And what does it mean? Neither too strong nor too weak means the reactants must get adsorbed reasonably strongly onto the catalyst to become active. And if they get reasonably and if they get adsorbed, what happens? If they are getting adsorbed by certain, some chemical bond formation will happen. Some other chemical bonds that were there in this reactant, that will become weaker, and those weaker bonds are now available for next reaction to happen, because if the bond is, this was a molecule which all the valencies were complete, this was a molecule, this was a catalyst, and its valencies were not complete here, the valencies were there, so three valencies. But in the molecule that is reacting, the reactant molecules, it's also valency, all valencies were complete. But once it is, now it has certain interaction with this, and it forms a bond because of the three valencies are there. Some bonds which get altered because of this bond formation, it will become weaker, and that weaker bond is called, that bond has been activated. And once that bond is activated, another molecule can go and then it can catalyze, and the further chemical reaction may happen because that particular bond is broken, and so some of the orbitals that will be now more available to a larger extent in the opposite direction, so that this reaction may happen. I hope you understand this. So the reactants must get adsorbed reasonably strongly. So if they get reasonably strongly, so the bond will be activated, where the reaction is about to happen, and the reaction is happening means some old bonds has to be broken, and that old bond has already been activated when this reactant is adsorbed on a catalyst surface. Once this reactant is adsorbed on the particular surface, some bond is already activated, means it became weaker, and that is the bond which has to be broken during the chemical reaction. So if the adsorption is stronger, so that bond will be more and more activated, and if that bond is more and more activated, so that reaction will be the barrier, because in the reaction. Why we see the barrier? As I have explained earlier, we see the barrier because a particular bond has to be broken, and because to break a bond we require energy, and that is why we see the barrier for a chemical reaction. And that barrier, since because of the absorption, that energy, that bond is already broken to a certain extent, that bond has already become weaker. So the barrier will now, for the breaking of the bond, now to break that bond we require lesser amount of energy, so the barrier is reduced. But they must not get absorbed so strongly that they are immobilized. So but what is important to note, that if those reactants they get, and the, maybe that bond is broken completely, a particular bond is broken completely, but these molecules which are now chemi-jobbed on the surface, and after the breaking those bonds, they are now, they sit there, they will be there permanently attached to that surface, and so they will, this process will not be a catalytic process, because for a reaction to be catalytic, the catalyst should be regenerated after a reaction, and if that chemical bond is too strong, then the catalyst surface will not be regenerated. So we also have to understand that this bond should not be so strong that the reactants that are absorbed there, they are immobilized, and the other reactants are left with no space of the catalyst surface for adsorption, and other reactants do not get a space to get adsorbed and to facilitate that reaction. And as you see this figure, usually what happens is this reaction was happening in one step, XY converted to Z. But when you add the catalyst, what we see, this catalyst is happening now, this reaction is happening in a multiple steps. And these steps, what we see, the all the steps, their activation energy is very low. And so although the number of steps increases, the catalyst changes the pathway of the reaction, the path changes, but all the reactions are now these barriers are surmountable at the room temperature or the normal temperature. So this process is what we call a catalytic process. So it has been found that the hydrogenation reaction, the catalytic activity increases from group 5 to group 11 metals, with maximum activity being shown by group 7 to 9 elements of the periodic table. So what is this point means, it is explained here with the example. So what we see from group 5 to group 11, group 5 is what, from the, I think, group 1 alkali metal, group 2 alkaline earth metal, group 3 this is the scandium, then titanium, the vanadium. So group 5 is the from the vanadium family to group 11 the platinum, where it belongs to platinum is the copper family. So they are actually, they act as a catalyst from vanadium compounds to to this copper compounds, all the family members, they behave as a catalyst, but what we see, their catalytic activity increases from group 5 to 11. So from vanadium, what we see in the same group, vanadium, then chromium, then manganese, then iron, cobalt, nickel, copper, and similarly you see in the other group members that this is the 3D group members, then 4D group members, 4D, 5D. I am not naming them because it is not in your syllabus. So just 3D members you just you remember, and that is enough for you. So what happens? The group 5 to group 11 in the catalytic activity increases, but what we see, the maximum activity being shown by group 7 to 9 elements. So what does it mean? So maximum activity is shown by group 7 to 9 elements. So group 7 is what? It's a manganese family. Manganese, then iron, then cobalt. Maximum activity is shown by manganese, iron, and cobalt family members. But what we see, that the catalytic activity increases, we are saying up to the group 11, means if you see the platinum is a group 11 family member, it is sorry, nickel, it is not copper, only up to the nickel family, not copper. So nickel, then palladium, and then platinum. So platinum is below nickel, and what we see, why we use platinum as a catalyst, this is because and the group 11 is actually, it goes up to the copper, that is fine. So what we see, this is because the activity, the catalyst, the members from group 7 to 9 elements, their catalyst, the valency that they create, this hydrogen forms and oxygen forms very strong bond with them, and because the strong bond formation, the catalyst is also destroyed, because the product, that molecules that they get absorbed are not very easily dissociable from the surfaces, and so they are not actually used as a catalyst. So we use as a catalyst, the catalytic activity is increased from 5 to 11, although maximum activity we see from 7 to 9. Although the maximum activity, when we see maximum activity means the bonds were broken very easily, activity is high, but what we also see is the slowly and slowly these molecules this are getting permanently absorbed on the surface, and so their catalytic activity decreases. So the hydrogenation of this reactions is H2 plus O2. We see this the formation of H2. We use platinum catalyst. This is because the 5 to 7 means this surface here the products will not permanently get absorbed, and so this is what we call about the activity. Now let us talk about the selectivity of a catalyst. The solid catalyst and any catalyst is selective. Suppose here we are talking about mostly the selective catalyst, and because it's the heterogeneous catalysis we are focusing mostly on. The selectivity of a catalyst is its ability to direct a reaction to yield a particular product selectively. When under the same reaction conditions, many products are possible. What does it mean? If suppose a reactant, a set of reactants are given there, and these reactants have possibility to form many products. It can form X, Y, and Z in three different directions, maybe mm, in some other direction, some other product. And they're saying so. If a particular catalyst is used, it catalyzes only one particular reaction, and so in the particular pathway, it facilitates the reaction to go, and that is called the selectivity of a catalyst. So selectivity of a catalyst is the ability of the catalyst to direct a reaction to yield a particular product selectively when under the same reaction conditions many products are possible, and in all the directions whatever the products are, they are thermodynamically feasible, they are spontaneous, the reaction is spontaneous in that direction. So catalysts are usually highly selective in nature. They can accelerate a particular reaction while inhibit another one. Selectivity of a different catalyst. This point we have seen selectivity of different catalysts for the same reactants is different. For example, as the same reaction, the selectivity starting with H2 and CO, what we see, and using different catalysts, we get different products. So CO and hydrogen, when they react in the presence of nickel, they form methane and water. So methane is formed in the presence of nickel catalyst. So this is nickel catalyst is selective. It is giving only one this exclusive product. However, carbon monoxide when reacts with hydrogen has also potential to form methanol, and it can also form formaldehyde. But in the presence of nickel, it forms only methane. But in the presence of copper, monoxide when reacts with hydrogen, it forms formaldehyde. And in presence of copper, chromic oxide or zinc oxide and chromic oxide, carbon monoxide and H2, it forms methanol. This reaction we have already seen. So this reaction actually the water gas. Water gas in the presence of copper catalyst, it forms formaldehyde. Water gas when reacts with hydrogen, because CO plus H2 water gas in presence of ZnOCr2O3 or copper Cr2O3 forms methanol, and with the H2 CO plus H2 water gas reacts with two molecules of hydrogen in the presence of nickel to form one molecule of methane and water. And water in the form of the steam. So water is steam, the gaseous. So thus it can be inferred that the action of a catalyst is highly selective in nature, and this selectivity is more for the solid catalyst. It has been seen in comparison to the homogeneous catalyst. As a result, a substance which acts as a catalyst in one reaction may fail to catalyze another reaction. So what we see, this substance which is catalyzing this particular reaction in one particular pathway, it is following to give this product, but it is not catalyzing this reaction. So it does not catalyze this pathway from this product. And so this is what we have seen, the selectivity of a catalyst. I'll stop here. The other points about the catalysis we will see in our next lecture. I hope you understood most of the points.